Welcome to the C2QA Quantum Thursday. We're glad you're here with us and could join us. My name is Evangelina Shreve, and I'll be your moderator today. I am the Director of STEM Education at Pacific Northwest National Laboratory, which we refer to as PNNL. PNNL is a Department of Energy national laboratory that is advancing scientific frontiers and providing solutions to critical national needs in energy, national security, and the environment. During the presentation, actually, at the end of the presentation, we will have some time for questions. At that point, we ask you to either put your questions in the chat box or to unmute yourself and ask the question directly. Now, it is my pleasure to introduce Karol Kowalski, a laboratory fellow in the Chemical Physics Theory Group at PNNL, who will be presenting today. Dr. Kowalski is leading PNNL's Basic Energy Sciences Quantum Information Science project. This project focuses on enabling quantum computing for realistic chemical stems and processes. He is recognized for contributions in the area of coupled cluster theory, including renormalized coupled cluster theories, multi-reference formulations, and linear response methods. An important part of his research portfolio is associated with the development of scalable implementations of many-body formulations. These formulations describe correlated behavior of electrons in molecular systems. In particular, Dr. Kowalski has developed implementations of quantum chemical methods. These methods are capable of taking advantage of hundreds of thousands of processors, which with the concurrent utilization of various types of accelerators. Dr. Kowalski is also an author of Green's function-coupled cluster formulations used in high-accuracy characterization of ionization and transport processes in molecules. Please take it away, Karol.
Evangelina, thank you very much for this very nice introduction. So let me start sharing my screen. I hope I will be as successful as 5 minutes ago. Let's go to the full mode presentation mode. So first of all, I would like to thank the organizer for inviting me to this, giving me opportunity to talk during this C2QA seminar series. And today, I will be talking about our recent developments in the context of the unfolding coupled cluster formalisms for dimensionality reduction of many-body quantum problems. So I will give you several examples how this formalism works in the area of quantum chemistry. So let's get started from the kind of digression, putting things into perspective. And in quantum chemistry, you can observe some kind of regularity in the way how computational paradigms are changing. You can see that from this picture that every 40, 50 years, there is a switch in technology used to model chemical systems. It started around 1927, early days of quantum mechanics with the valence bond theory, and for this purpose, the analog computers were used, most likely the well-known slipsticks. Young generation might not even know what it is and how to use it. Around, 40 years later, people, got quantum chemists got access to the first digital efficient digital computers, and around 1968, you could see the growing number of papers reporting more accurate, more accurate calculations using digital computers. And finally, in 2018, we had the first real demonstration of the quantum computing. This is new emerging technology on the real hardware. And what is very interesting in each case, the primary target, the first victim of the research was a hydrogen molecule. And if this trend is sustainable around 2070, we should see another interesting stuff looming on the horizon. And I bet the first applications will be to the hydrogen molecule as well. So why should we care about the quantum computing in general? I mean, we all know that the quantum computing is mostly advertised on the basis of the possibility of breaking certain computational barriers. in quantum chemistry, which cannot be properly addressed using classical computers. This is associated with the exponential growth of the variational parameters we have to optimize to get the accuracy. But from my perspective as a quantum chemist, another very important feature of quantum computing is the fact that you can get a uniform level of accuracy in the energy predictions for a broad range of different molecular situations and the complexity of the wave function. So this is my favorite example, famous H10 molecules, which has been recently intensively explored and studied with different methodologies. So interesting feature of this model is that you can change the distances between the hydrogen atoms, and by changing this distance, you can go from the weakly correlated regime where the wave function is, the form of the wave function is very simple, to the strongly correlated regime, where the multi-reference or quasi-degeneracy effects play a really important role. And as you can see from this picture, many advanced formalism like coupled cluster, single reference coupled cluster, or the multi-reference coupled cluster methods fail. And it's interesting to notice that at the same time, formalism like phase estimator give for all the distances a very good level of accuracy, which is not dependent. It doesn't depend on the structure of the underlying wave function. So the same accuracy can be achieved both for the weakly correlated as well as for strongly correlated regime. So I've done following techniques, which is a primary target of my talk today. Subject of my talk falls into category of hybrid algorithms. So the question is, there are many definitions of hybrid algorithms. I'm inclined to use the simplest one. We basically take the most appealing features of the quantum and classical computing and to amplify the accuracy of our predictions. There's a long list of those methodologies. Last week we heard from Sophia Alkinomou talk about the VQE methods, which is one of the most important examples of the hybrid methods. But there are some other formalisms which differ from VQ in the way how they use quantum versus classical resources. So we have subspace algorithms which have been recently used, also extended to the excited state methods. There's a lot of action happening in the real and imaginary time algorithms. Recently, these methods were used to calculate green function, time-dependent green function on the quantum computers, and reduced dimensionality approach. So basically, in the reduced dimensionality approach, we're trying to squeeze the dimension of the problems to match the existing quantum resources. And the progress is really significant, and there are many other formulations I haven't mentioned here, but probably in a year from now, this list will be already obsolete. So downfolding methods is coupled cluster downfolding methods uses the classical resources in a slightly different way than, for example, VQE formalism. So basically, on the classical machines, we are storing the so-called external part of the wave function, or external parameters to define the wave functions. They are used to construct effective Hamiltonians, or the active space representation of effective Hamiltonian. And in the next step, the effective Hamiltonians are mapped into the qubit register and being solved using your favorite quantum solver. So this framework gives you a lot of flexibility, talking about tuning to the existing quantum resources. This can be achieved by changing the size of the active space. It also gives you an opportunity to really take advantage of the high-end computational resources on the classical side. You can think about the petascale or exascale machines to build the effective Hamiltonians. So the effective Hamiltonians, actually, theory of effective Hamiltonians is almost as old as quantum mechanics. It started in 1929. Van Vleck used the first type of unitary similarity transformation to solve the problem for the diatomic molecules. In 1950, Foldy, Woodhausen used the similarity transform Hamiltonians to decouple the low energy and modes in the direct equation from the high energy modes. So this was followed by many developments in the following years. From my perspective, the really important areas where you can find the effective Hamiltonians are those extensions of the coupled cluster to the multi-reference problems that can give you a tool to describe the challenging open shell systems in the molecular world. So you can see several formulations, specific formulations of the coupled cluster theory in the Fock space, in the Hilbert space, and also canonical transformation theory. Those methodologies are kind of permeating to also the nuclear physics. Those methods are very universal in the sense of the interactions defining the systems, and probably in the few years we'll see pretty advanced applications of those methods in nuclear structure theory. Also, recently we saw several interesting papers looking at those problems from the perspective of quantum computing. So I should mention the Bravi Di Vincenzo Loss paper on the Schreifer-Wolf transformation, and pretty recent Rolando Soma, the Hamiltonian situations in the simulations in the low energy subspaces. So downfolding techniques, the way how you construct effective Hamiltonian is associated with the form of the wave function, underlying ground state wave function. And today I'm going to tell you about two possible exponential parameterizations of the wave function. One is commutative. This is a standard coupled cluster theory where the wave function is represented in the form of the exponential ansatz, where T is a cluster operator acting on some reference function, which is called, it is chosen as the Hartree-Fock. This is nice commutative case, but it's well known that this function, this form of this representation of the wave function is not normalized. We have also the second parameterization, the exponential type of parameterization of the exact wave function in the form of the double unitary coupled cluster ansatz. This is a little bit more complicated because the algebra defining those external and internal cluster operators is non-commutative, but the good thing is that wave function is normalized to union. No matter what kind of exponential representation of the wave function are you using, you can always define based on that active space representation of the effective Hamiltonian, which can furnish you with ground state energies. So this also gives you the idea, a different way of looking at the coupled cluster methods as a specific form of the normalization technique or Levin partitioning methodology. So to understand what is going on with the unfolding, let's start with the standard coupled cluster theory, single reference, where the T operator may contain different types of the collective excitations there, singles, doubles, triples, which defines the hierarchy of the coupled cluster methods. You can have CCSD with singles and doubles, CCSDT with triples, quadruples, and so on. So this hierarchy of the approximation can give you more and more accurate energies, of course, at the higher cost. I mean, CCSDTQ scales really high with the number of bases, set functions, or system sizes, n to the 10th. And if you cannot properly define the reference function, the exponential coupler cluster parameterization is the best engine for the error propagation. So that's why we need quantum computing. So let me quickly define basic operators used in our analysis. We are working in the particle Hall representations. We define the excitation operators as basically the strings of the creation of electrons in the virtual unoccupied states and the annihilation of those electrons of electrons in the occupied states. In the particle Hall representation, this is a string of the creation of the particles and creation of the holes. When this excitation operator acts on the reference function, you are getting excited Slater determinant. All those excitations are commuting, and they are part of the commutative algebra Gn shown here, generated by those elementary excitations. Very important from the point of our analysis are the subalgebras. So basically, subalgebras are generated by the generators, which can reproduce all possible excitations within the active space defined by the subset R of occupied active orbitals, and subset S defined by some active unoccupied orbitals. So they are usually denoted this way. One means that there's one orbital in the one active occupied orbitals. 4 means that there are 4 active virtual orbitals. So if S part is skipped, like here, it means that all the virtual orbitals are considered as active. So those subalgebras play a very important role because they instigate, they induce the partitioning of any type of the cluster operator into the internal part defined by the amplitudes that only are defined by the active spin orbitals, and external part defined by amplitudes with at least one inactive orbital. And for us, the most important class of those subalgebras are the subsystem embedding subalgebras, where the internal part of the cluster operators generates form of the full CI expansion without the active space. So using this SES approach, you can show that for any approximation or full variant of the coupler cluster formalism, you don't have to calculate energy in the way how it's described in the textbooks in the standard expression for the energy. Instead, you can get the same energy by diagonalizing effective Hamiltonian in the corresponding active space. This effective Hamiltonian in this case is non-Hermitian, where the internal part of the cluster operator defines the corresponding eigenvector. So the downfolding theory gives you a precise descriptions how those smaller effective Hamiltonians have to be constructed, and based on this result, you can say that you can probe the composite quantum system with any with the Hamiltonian effective Hamiltonians of any subsystems, or any subsystem just described by the corresponding subalgebra. So in the extreme cases, you can, for example, for closed shells, you can use the subsystem composed of 2 entangled with the system electrons in, for example, 2 orbitals. Now, all those constructions are very reminiscent of the, especially for physicists, the renormalization procedures. And this is also because if you look at the definition of the effective Hamiltonian, you see that in this problem, the internal degrees of freedom are decoupled from the external degrees of freedom, and external degrees of freedom define the whole surroundings of our subsystem. the rest of the composite system. So, you can see that the effective Hamiltonian explicitly depends only on the external parameters. So what is even more, if you, by the way, it's so interesting, if you really are interested in recovering standard coupled cluster energy formulas, you can apply this trick for the subalgebras which contain no excitations, right? So then you recover the standard formula. What is very interesting and was actually very interesting to analyze this property. This is valid for any subsystem algebra, so for any subsystem of the composite system. So there are a lot of those subsystems you can define, and for example, for the closed shell systems, they are proportional to the 2 to the power of the number of the virtual orbitals. So the question is how you can utilize this knowledge, and how you take advantage that actually you can represent something in the form of the small dimensionality subproblem. So there's a very interesting way we have explored some time ago, 3 years ago, when the first paper was published. So you can couple those small dimensionality problems for different this effective Hamiltonian problems for the different subalgebras into the flow. So basically, you have equations composed of the coupled small dimensionality eigenvalue problems for different subsystems, or for different algebras, or for different active spaces, complete active spaces. The downfolding procedures defines the way how those problems should be communicated. So what kind of information has to be exchanged between those systems in the flow equations when they're coupled into the flow. So the power of the coupled cluster method is the fact that actually you can show the equivalence of this representation to the standard form of representing coupled cluster equations in the form of the connected diagram shown here, with the cluster operator defined as a unique as a union of the unique internal excitations corresponding to the different eigenvalue problems. You can look at this results from the different perspective. You can say that inverse is also true. So if for the specific choices of the cluster operators, you can represent the big problem in the large space, subspace of the Hilbert space. You can represent this big problem in the form of the flow, or in the form of the coupled small dimensionality eigenvalue problems. So this gives you an option how you want to solve the problem. If you have a big computer like Summit or whatever is looming on the horizon on the exascale, you probably would be using this, because this problem is you can really efficiently factorize it, and numerically it's probably more efficient to solve the problem in this way. But if your computational resources are limited, probably this pipeline is more efficient, and basically the maximum resources needed in these flow equations are defined by the largest eigenvalue problem, by the largest computational block involved in the flow. This also gives you the alternative way of looking, new way of looking at the reduced scaling methods in the quantum chemistry. For example, if you define the flows based on the occupied orbitals, which kind of define the pair, or the pairs of the orbitals, or each computational block is defined by the well-defined effective Hamiltonian. And for this reason, you can precisely define the density matrix for each sub-blocks and use it for example, a selection of the most important amplitudes. And also, it turns out that the pair problem is no longer a pair problem, it's a 4-electron system. And in this way, you can actually, in addition to singles and doubles, you can introduce in the controllable way classes of triplets and quadruple excitations. And basically, those features have to be postulated in the theories, local formulations like DLP and all. So to get the Hermitian form of the effective Hamiltonian, and we're now going towards the second parameterization of the wave function. We use this double unitary couplet cluster formalism, right, where the sigma external and sigma internal are the anti-Hermitian cluster operators. In this notation, the subalgebra H is used only to define the active space, where the, for example, with respect to which external and internal cluster operators are defined. So when we published, when we submitted our paper on first paper on this, we assumed that this this expansion is exact. But in the following papers, we were asked to show this the exactness of this, and for this purpose, we used this products of the elementary rotations to basically eliminate certain types of the configurations, and we can easily show that using this trick, we can reduce the full wave function to the part which is defined only in the active space. But this is the only case where we use those tricks, and actually, in some applications, we don't even to use the quantum phase estimator. We don't need the knowledge about the sigma internal part. So using the similar tricks as the single reference couplet cluster theory, we can show that using this double unitary couplet cluster formalism, we can again define the for a given subalgebra of active space, we can define the effective Hamiltonian, which can give you produce the exact energy of the system, assuming that you know exact form of the external sigma, the external cluster operator, and assuming that you can form the exact form of the effective Hamiltonian according to this prescription. So we should be aware that this is a way more challenging case than the single reference theory, because now the generators used to define the sigma externals are non-commuting. So in the real world, if you want to use the real world, you have to use some approximate form for this operator, because in general, this is non-terminating expansion. So we are considering in our work several approximations associated with the major features of the effective Hamiltonian. So the first is, of course, the length of the commutator expansion. In general, this is infinite expansion, non-terminating expansion. So you have to be driven by a certain principle how you basically truncate it. So in the current implementations, we are using the single commutator expansion with certain sets of the with certain subset of the terms coming from double commutators, and this is because we want to basically assure the perturbative consistency of the Hamiltonian expansion. We can go in next step to the double commutators with some parts of the small class of the triple commutator terms, which again gives you consistency with respect to certain perturbative order of this expansion. Another important issue is associated with the rank of the many-body effects included in the unfolded Hamiltonians. Right now, we are using 1- and 2-body interactions. Of course, there are 3-body interactions and higher there. But you can show that if the active space is getting bigger and bigger, those terms are getting smaller and smaller. I mean, again, this is depends on the way how you approximate the external part of the cluster operator. But in some cases, the inclusion of 3-body terms might be necessary. So we are trying to figure it out now. Another issue is a source of the external amplitudes. You can show that for the large active spaces, approximating the external cluster operator can be done using the unitary standard unitary couplet cluster formalism. For practical reasons, we chose the T external in the sigma external from the CCSD, the external parts of the cluster amplitudes obtained in the CCSD calculations. But using NWChem, you can extend it to higher order couplet cluster methods and even some classical type approximations for the unitary couplet cluster. Equally important is the orbital choice, and I will get back to this issue in the following slides. So this is our first demonstration of the efficiency of the downfolding Hamiltonians that has been performed using NWChem and quantum development kit developed by Microsoft Quantum team. And this is a H2 molecule in the CCP-VTZ basis set, full set of orbital contains 30 orbitals. But we would like to basically use the downfolding techniques and build the effective Hamiltonian in the active space composed of the 4 orbitals. So how it works? So the red curve shows you the full CI results in the small active space for orbitals. The blue curves show you the full CI curves obtained when all 30 orbitals are correlated, and the green dots are the results obtained with the effective Hamiltonians, downfolded Hamiltonians in the active space defined by 4 active orbitals. So you can see that results are pretty good and pretty close to the full CI results, numbers, energies. And again, I mean, this result have been obtained using only 4 orbitals, so you can really afford, now these days, you can afford those simulations even on the real machines. This is yet another problem. We use a different solver for solving the downfolded Hamiltonians for Li2, potential energy surface. This is actually a pretty nasty system because if you are using Hartree-Fock orbitals, the active space is pretty large if you want to get it right. So at least you have to have either 7 or 10 orbitals, right? And 10 orbitals is mostly dictated by the availability of the resources, quantum resources. So if you do the C2QA methods, which is very close to full CI, not shown here, you're ending up with this curves. If you do the downfolded Hamiltonian calculations for the 7 and 10 orbital space, they are better, but actually those curves look pretty nasty, right? And then we decided to use the natural orbitals, this green line, which are very nice. I mean, this is a very low level of the natural orbitals where we use MP2 theory, but you can see how much better results are now. So especially for the equilibrium region where the natural orbitals based on the MP2 expansion are well defined. And this gives us kind of rationale to go towards the different types of the orbitals. Right now, Nick Bauman is working on the MCSTF orbitals, but there is also a possibility of using DFT, natural orbitals, and Bruckner types orbitals, which are especially interested from us because those all correlated orbitals, which give you the largest overlap of the corresponding Slater determinant with the correlated wave function. So this is yet another experiment we perform for N2 and C2H4 benchmark systems using VQE algorithms for the generalized unitary couplet cluster parameterization. It turns out that those generalized unitary couplet cluster methods are more accurate, but they are of course using more amplitudes, more parameters compared to the standard unitary couplet cluster. But for N2, for example, you can see that the downfolding methods can, even though you are using the couplet cluster as a source of your external amplitudes, they are offset the variational breakdown of the CCSD theory. This is yet another example here to the right, ethylene 48 total orbitals. But you can see the scale of improvements when you go to standard diagonalization using the bare Hamiltonian in the active space to the diagonalization of the downfolded Hamiltonians in the same active spaces. So the message to take home is that you can recover around 90% of the correlation energy using very simple forms of the Hamiltonians based on the single commutator expansion, right? In the following years, we are going to make those methods more accurate. So talking about the freedom of choice of the various solvers, we recently embarked on the new type of the quantum algorithms based on the connected moment expansion, which was introduced around 1987 by Kozlowski. This is kind of consequence of the earlier analysis of the imaginary time evolution called T expansion, where you can show that the asymptotic behavior of the energy can be expressed in terms of the so-called connected moments defined here. So there are very simple functions of the standard moments. I mean the expectation, the values of the powers of the Hamiltonian, and very closely related to this. Those problems are yet another formalism, Peter de Vries Soldato functionals, where the ground state energy is the lowest root of these polynomial equations, where the coefficients are calculated by solving the linear equations, where the matrix M and vector B are basically expressed in different rank as a different rank moments, the standard moments, right? So if we the only caveat behind those methods is that in each case you have to provide the reference function, which has non-zero overlap with the exact wave function. And to build the effective quantum algorithm for those methodologies, you have to have efficient algorithms to calculate those standard moments. Expectation the values of the powers of the Hamiltonian. So we started very simple just to see how it works, right? So we use brute force methods, and we basically use the Hadamard test to calculate expectation values of those UJ strings, this product of the different Pauli strings coming from the Hamiltonian, which can be reduced further to the Pauli strings with appropriate phase factor in general. And we show the first examples on the H2 model, very simple H2 model, and the single impurity Anderson model. In all cases, we used several variants of the connected moment expansion, shown in the top pictures. I mean A and B here, this and this. But also we explored the PDS formalism, which is the most efficient of all of them. Basically, you don't have to go to high order of the PDS expansion. When I'm talking about the order of the PDS expansion, I mean that for the order k, I have to calculate the moments 2k up to moments up to 2k plus 1. So of course, the biggest challenge in this approach is the number of measurements, but this can be really efficiently reduced by using different types of tricks like qubit-wise commutativity, general type commutativity, a new class of quantum power methods introduced to calculate the powers of the Hamiltonians, and the possibility to play with the direct block encoding of the Hamiltonian powers. But these methods also offer you kind of new way of looking at the problems, because, for example, the PDS function is correlated. You can try to integrate low rank DQE methods with those correlated type of the Hamiltonian. And what is a really great advantage of this in the single shot calculations, in this kind of combined calculations, you can get information about grounded excited states, because I forgot to tell you that the higher roots of this polynomial provide the upper bounds for the excited state energies. So there's a light in the, recently we performed a number of tests which show there is a light in the tunnel, talking about the number of the measurements needed to get the energies. So we performed tests for the linear H4 molecule and now I don't remember the basis set. It was T21G probably, something very simple. But instead of this exponential growth in the number of measurements, you can see that if you keep track of what has been measured, this is the caching algorithm. After the power, fourth power, you don't need to measure anything new actually to get all you need to calculate higher order moments. And this is very, very important message, because this is something which really can reduce the number of the measurements in your system. And this is the scale on the bottom panel. You can see in the bottom panel, you can see the scale of the improvements. If you take, for example, some variant of the adapt VQE with certain types of the excitations included, you're getting the errors shown by this full green bar. If you use the same ansatz, the same trial wave function, and in the context of the low rank PDS formalism, your errors are reduced by a factor of 5, 6, 7, depending on the system. There's another very important feature of using correlated functionals in the context of the VQE methods. So Sam Karol came up with several kind of benchmark studies of and benchmark Hamiltonians to study the performance of the VQE solvers. And as you can see, using trial wave function, which is parameterized by 2 parameters, θ1, θ2. Thanks to that, we can really nicely plot what is going on. And you can see that whereas there are regions in the configurational space, in the parameter space, where you start from any point in that region, there is a high risk that you are never get to the ground state energy. If you look at the same landscape of the energy, looking for the combined PDS VQS methods, by the way, we have already the analytical gradients of this approach implemented. You see that no matter where you start from, you always get into the ground state energy. So this might be yet another kind of alternative way of coping with the barren plateau problem. So here in this panel, we have a very recent, still preliminary simulations of the Heisenberg system, Heisenberg model. On the quantum hardware. This was IBM Toronto, as far as I remember. So Bo Peng developed those methods, and he's also the first author of those analytical gradients for the PDS VQE formalism. So I guess it will it's a very interesting alternative to get very accurate, pretty accurate results with the when we combine the correlated form of the functional with the low rank of the VQE trial wave functions. So downfolding methods can be also used in the context of the excited states. If you know the information about the external excitations for the some case excited states, you can get pretty good estimates of the excited states. I mean, excited states problem is more, of course, sensitive to the accuracy of those sigma externals. So there's some extra work needed to get there. But I guess we can capitalize on the high rank EOM kappa cluster methods implementations. But there are some situations where you don't know anything about the sought after state. And we recently demonstrated with the Microsoft team that actually for identifying the high energy X-ray states, quantum phase estimators can be very, very useful, especially in the context of of those complicated states, satellite states, which require high level of collective excitations. And this is in line with ongoing effort at PNL to deploy classical implementations of quantum approximation. I mean, of the quantum chemistry methods to define spectra, for example, for the X-ray photoelectron spectroscopy, using either green function, coupled cluster green function, or the cumulant theory, especially for the open shell states. And for this purpose, we need something else. And we recently developed a time-dependent version of the downfolded Hamiltonians. We assumed for a starter that orbitals in the reference are time-independent. We use the same external, the doubly unitary expansion, now time-dependent. And you can show that within an active space of interest, if only you can give some good approximations of the external part, the dynamics of the whole systems is defined by the dynamics in the of the system in the active space defined by the effective Hamiltonian. So let's switch the gear and move a little bit back and try to talk about how we can define the flows for the double unitary coupled cluster method. So how basically we can make those possible different active space problems talking to each other in the way they can basically probe. When you put them together, you can, in analogy to the single reference methods, you can probe a larger space than each of this block individually. And we recently published, I put papers into arXiv, basically defining how the flow works. So basically, we can partition the large problem into the number of smaller active space problems. And in this way, we can basically probe much larger subspaces, either in the active spaces, which you cannot deal with today, or for enlarging the basically virtual space probed in the quantum algorithms. Those methodologies are size extensive. This is very important from the chemical applications, and the unfolding methods define rigorous communication protocol, how those subsystems talk to each other. And it's very interesting will be very interesting to see how it works, especially for the local methods where there were problems, previous problems with the mapping Hamiltonians to the qubits. So, and the most important, I mean, the quantum resources, the required quantum resources are associated with the largest sub-problem included in the flow. So this is in full analogy with the reduced scaling methodologies for the single reference case. So it takes us to the conclusion. I'm slowly running out of the time, and I would like to leave for 10 minutes for the discussion. So this is the main conclusions of my talk. So downfolding techniques can be used in the different variants to reduce the dimensionality of the quantum problems. They can be used to describe the ground and excited states. They can also be extended to the time domain. They basically can be viewed as renormalization techniques. They can provide you the communication channels between the different sub-problems. And when they're organized into the flows, they can be used to probe large subspaces of the Hilbert space. Talking about the possible extensions, excited states, quantum dynamics, local formulations, and connected moment expansion. This is something we are really looking at currently. And for this purpose, we will pretty soon release the kind of library for pre and post process of quantum information for the purpose of dealing with the connected moment expansion. So this is all I have for today, but last but not least, acknowledgement. I would like to really thank my colleagues and collaborators for PNL, from the BSQIS team, and from the Microsoft quantum team. This is a really prolific, this is very great collaborations, and we're jointly able to do much more than we would be able to do individually. So this tells you about the, the ongoing collaboration. And also, I would like to acknowledge the sources of support from the BSQIS project program from Quantum Science Center led by Oak Ridge. This is a part of National Quantum Information Science Research Centers, and for source from support from LDRD Quasar project at PNL. So this is my last slide. Thank you for your attention, and I guess we have still 10 minutes for questions.
Thank you, Karol, for your presentation. Now we will open it up to questions and answers session. And if anybody has a question, they can feel free to unmute.
I had a question about complicated molecules, like simple molecules like C2, but might require a very large basis set. Could those be addressed in your formalism, or it just gets, you need too many qubits to handle something like that?
Well, I mean, depending how big basis set can you use. I mean, for Li2, which is also kind of C2 level of problem, we found very useful, to use the correlated orbitals. They basically can really nicely squeeze the correlation space, right? Probably something like that could be possible for C2 if we use some form of the natural orbitals, but of course we have to try to see how it works, right? So basically, right now I see the application of the different downfolding methods tightly connected, strictly connected with the use of the right orbital. So basically, if we can build an active space which is smaller than, say, 10 orbitals or so, we should be able to tackle this problem. I mean, C2 is a big problem, and many people were really struggling on the classical side with this problem, and multi-reference CI, different types of the couplet cluster methods, renormalized active space, and so on and so forth. But I guess a proper choice of the orbitals might help you in at least making this active space smaller. So this is my answer. In the flow equations, this should be easier because we can couple several smaller active space to basically probe a bigger active space. And this is the way how this just general active space methods are being developed these days. So I don't know if this answers your question.
Oh, that's terrific. Thank you. It looks like that you're optimistic then on near-term hardware. You could do something like this.
No, basically, we have to be cognizant of the limitation of the hardware and basically build approximations that can be tuned to this hardware. I mean, how it can be done, it's just, it's this is defined by our understanding of the theory. But for example, if you can, in the flow, in each particular block, you are okay with doing with the 10 orbitals, I guess it's fine, because 10 orbitals, give or take, can be handled with existing hardware. And as I said, if you have coupled block, you never go beyond the 10 orbital limit, for example, right? So this might be an interesting concept to follow, and we explore those methods on the classical side, and they work pretty efficiently. So I can see no reason why they shouldn't be working, those concepts working in the case of the quantum computing, even if you have limited resources. And I hope over the time, around 2070, we should see something really more stable, right?
Thank you very much.
Thank you for your question. We have time for another question. Feel free to unmute yourself and ask the question if you have one. Let me check the chat box. No further questions in the chat box. I believe there's no further questions, Carol. I'll go one more time. Any other questions from the audience?
I just had one more question because you mentioned the H10 system. As you increase the number of atoms, at what point do you do better by using like a tight binding approximation or something that we use in like nanoscience or condensed matter?
Yeah, so actually this is a very good question because I didn't have time to expand on this, but there's a recent paper published in the Physical Review Letter. So it was kind of benchmarking the H10 system with different various methodologies, right? And actually those methodologies you are mentioning and some others might work pretty well. For example, a different type of the green function embedding methods, which is not that far from what methodologies you mentioned, have a great potential to work well in those challenging situations, right? I mean, of course, the problem is the number of active orbitals in this type of the green function of self-energy embedding or related methods. The number of the active orbitals is the half of the number of total orbitals. So, well, more tests have to be made if you know those methods can be applied to larger, I mean, strongly correlated systems. Because H10 for at the large geometries, I mean, basically for the Hartree-Fock molecular basis, you have to define all the orbitals as active. But as I say, there are some approximations on the classical side which are very, very promising. You know, we don't know how big active spaces will be really needed in the realistic simulation. Right now, there's a half of the 5 active orbitals out of 10 had to be used to get a good level of accuracy.
Okay,
Thank
thanks.
you, Dr. Thank you for your question. Dr. Kowalski, thank you so much for your presentation today, and we really appreciate everybody joining us for Dr. Kowalski's presentation. We welcome you to continue to attend the C2QA lecture series. Thank you, everyone. Have a good day.